All right. Yes, so hi everyone. I'm Greg, co-founder and chief exec at undo.io. They don't let me write much code anymore, but back in the, still write a little bit, and back in the day, trying to get undo to work, which is this time-traveling debugger, we need to capture, to make the time travel debugger work efficiently, right? That is the ability to wind back to a previous point in an execution of a process. We needed to capture everything that the process does with the outside world. Basically, all the interactions between the process and the kernel, right? So all the system calls and the thread switches and the signals and everything, they all get stored in a log, and then when you want to go back in time, it goes back to a snapshot, plays that forward, and replays, like redoing exactly those things that we saved. And it turned out to be quite eye-opening. I thought I understood, before I went on this journey, I thought I understood what the operating system was, what the kernel was, how that interacts with user space, and it turns out that I totally didn't, right? And it's like, it's one of those things that it's quite close to the programmer's model. If you're programming in C or C++, you get this kind of model of the operating system that you're coding to, and it's one of those things that's like, it's sufficiently close that it's very confusing. It's the uncanny valley, right? So you think you know what you're doing, but actually the details underneath are quite different. And this matters, I think, for not just if you're trying to implement a time travel debugger. It matters when you're trying to debug something that's gone mad, right? If the debug is, it's all working and we can add logging statements and we can use the debugger and everything's working fine. But sometimes, everything is just completely mad. We don't know what's going on. Something's deadlocked. We want to attach to a running process. We want to, strace and see exactly what's going on. And if you don't understand the real interaction between your process and the kernel, things can get very confusing. And if you do understand it, you can start to do certain tricks. So I'm here to share some of that today. So we have like half an hour talk, 25 minutes left. I'm very happy if anyone wants to ask questions at any point. By the way, I always have an objective with every talk that I do to learn something. I want to come away from the talk knowing something about the talk that I didn't know on the way in. And when I talk to audience like this, there's always something I can learn, right? So anyone can, if I'm wrong or missed something or there's an adjacent thing, just shout it out. I'll repeat the question if I can remember. Oh yeah, and if you want to take a photo of this QR code, you can win a free license. I'm going to a raffle for a free license of Undo, which is worth $7,900. Actually, it's not. It's worth a lot more than it costs $7,900. And in fact, I think in this raffle you get the whole thing. So UDB is like a kind of just the debugger. You get the whole thing with live recorder and everything, and it's completely awesome. You should just enter the raffle. I'll put the QR code at the end just in case you haven't got time. I'll let people take the photo. And then there's no more marketing, I promise. Right, okay. So we're going to look at the process boundary, how libc interacts with the kernel, what we mean by kernel even, right? How are we defining this thing as the operating system? Looking at vdso, we're going to look at errno signals and some other stuff if we get time. We've got I could just talk all night on this stuff, but I'll expand and compress based on how we're going for time and how many questions I get asked and tangents we go down. Right, so this is the first thing, right? So programs talk not to the kernel, to libc. I mean, the first thing I would sort of point out here, the man page or man pages are wrong, right? In pedantic but subtle ways, right? So if I want to look at man to write, so this is part of the standard C library. It's write to a file descriptor. We all know what this does, right? But if I look at the man page sections, oh my God, can anyone remember? Who's your man? What are the, yeah, right, sections. So that was man 2, so it's supposed to be system calls. So the section 2 in the man page is supposed to be all the system calls. But that write, there is a system call called write, okay? But it's not that. That's not the system call. That's the C library wrapper to the system call. And it's almost the same, but not quite. And depending on the system calls, some of them are like more almost or less almost the same. So when my hello world program calls write, it's going to call through libc. Let's see what that looks like. So I've got a kind of hello world here, but this is Apologies, not C++. But anyway, so, and I've just gone as low level as I'm kind of going, as I feel I want to in the C code. So I'm calling the right system call directly rather than printf or anything else, okay? You should always use -G3, by the way, because it's just better. So let's have a look. Here's a neat thing, by the way. You can just go, I learned this relatively recently. Start I is like start, but it starts right at the very beginning of the program execution. So way before main is called. Like loads of stuff happens before main is called, and like global object constructors get called, and lots of setup stuff gets called. But this is before any of that's happened. This is right at the very beginning of the program execution. Another cool thing you can do in GDB, this is not really a GDB talk, but just to show the way around, is catch syscall right. Anyone use catch points in GDB? 1 hand, 2, 3 hands. It's quite cool. You can do various things. Whoops. Let me make it a bit bigger. So I can catch syscalls. I could just catch all syscalls. By the way, you can catch exceptions, except don't ever do that in GDB because that's an ADA exception. That's not what you want. You want catch or catch throw. Anyway, I'm going off. That's not relevant to this call. Catch syscall right, and then I can just continue. So this is the system call. This is where libc is calling into my program. If I go Control X2, that's the assembly code. Let's get if I go Control X2 enough times, I get the assembly and the registers, which is quite nice. Do I get the register I want? Yeah. So what's going on here? So the debugger, by the way, all of this is kind of useful if you're doing strace or anything. It's just we're using the debugger to see what's really going on. So we've got this syscall instruction, and the program is like right after the syscall instruction. Only it's not, actually. It's kind of before the syscall instruction has happened, and you can tell this because I think this only works on x86. It doesn't work on ARM. If I look at the RAX register at the top, its value is -38, and everyone knows what -38 is in an errno, right? It's errno-sys, right? It says the system call doesn't exist. So it's this really nasty hack that if you're stopped inside a system call, ptrace will return that the AX value, which is where the syscall number or the result goes, is -38. That can't be true. It can't be stopped in a system call that doesn't exist. So it hasn't happened yet. Now, when I go step I, in fact, yeah. So when I go step I, so this is the write system call. So it's going to write hello world. I'm going to go one instruction. Cool. So it didn't really move, except it did print out hello world and then TUI mode scribbled over the top of it. But and now if I look at the registers, RAX, which is the return result, now that's 15. Okay, so that's returned the value 15, which is kind of what write does. It returns the number of bytes that were written. So what's the difference? Well, in the write system call, the only real difference is the error handling. Okay, but when write fails, if we look in the man page of the system call, it returns -1 and sets errno, right, which is this global variable. Well, there's no such thing at the kernel level. So if it had failed, it would have returned a negative errno number in that RAX, and then the libc wrapper will stuff that into errno. We'll talk a little bit more about errno later on, because it's not really part of the ABI, but it is part of the kind of C model. Okay. So let's just back up a little bit, right? So, yeah. So what is a kernel anyway? So a kernel, in its general, not just specific to Linux now, I think it's a bit of the operating system, and it does either one or the other or both of these things. So it could do security and protection, and or it can give you kind of services like network and file system and stuff. If it is a microkernel, then it's only going to do security and protection, right? That it's not going to provide any services, but it is going to allow you to make sure that process A is protected, it's isolated from process B. Process A cannot read process B's memory, it cannot write to its memory, it cannot interrupt or corrupt it in any way, cannot see its resources, it cannot see the files unless it has permissions to, and the operating system is providing that kind of isolation, right? The only thing it can really do is timing stuff. So obviously process A could steal CPU resource from process B, but apart from that, it should be completely transparent if it's a protected operating system. Not all operating systems do this, right? So embedded RTOS type operating systems often don't. MS-DOS, for those of us who are old enough to remember that, didn't do any of the protection, it just did the services stuff, right? Real kind of, yeah, RTOS, real-time operating systems, sometimes just do services. Microkernels like Unix and other things just do the protection, security. The Linux kernel is what they call a monolithic kernel, and it does all of the things, okay? Now, lots of stuff does get done in libraries rather than inside the kernel, but it provides nearly all the networking and the file systems and all kinds of stuff. And when we do a system call, what's happening is the CPU is transitioning from what's called user mode to kernel mode, sometimes called supervisor mode. And really, there's only a couple of differences between user mode and kernel mode. The main one actually is there's certain instructions that if you try and execute them in user mode will generate a fault. The processor won't let you do them because they are privileged instructions. So if you try to disable interrupts, for example, if you're not running in kernel mode, then the CPU will probably say, no, you can't do that, because that way you could completely take control of the system and not let anything else run. And then with modern architectures, you often have certain bits of memory, certain pages, which are marked either accessible only in supervisor mode, kernel mode, or in user mode. It's all kind of changed since the Spectre and Meltdown attacks came along. So they kind of changed the way that when you call from the user mode into the system, into the kernel, it used to be that the address mapping, the virtual address mapping, kind of stayed the same. It's just that now you're in kernel mode, so you can access all these pages that user mode couldn't see. And then that turned out, because of like Spectre and Meltdown type stuff, to be a security vulnerability. So these days, the kernel will do a complete switch of the address space. So in modern Linux, really the only difference between user mode and kernel mode is there's just a subset of instructions that you're not allowed to execute in user mode. We call in to kernel mode from user mode via this syscall notion, system call notion, and that is CPU specific. I've documented here 32 and 64-bit x86 and 32 and 64-bit ARM. Just of course, there are many others, but that you can see how kind of they're all basically the same, but a little bit different. So the way that you do, actually, there's a bunch of ways you can do a system call on 32-bit x86. This is kind of irrelevant. There's not much 32-bit x86 code out there, but there is still some. The original way was this int x80, so this is a software interrupt, and then that will cause the CPU to change stacks and memory and all kinds of stuff and switch into the kernel in a kind of atomic way, right? The way the user mode calls into the kernel and then gets control back must be atomic, otherwise we lose the protection and the security side of things, right? Then it turned out that int x80 is really slow, and so then Intel and AMD introduced faster ways to do it. The Intel and the AMD ways on 32-bit are different. There's syscall and sysenter. It's probably a detail that no longer is relevant to many people. Everyone's just using 64-bit, and they can just use the syscall instruction, which is kind of sensible and does mostly the same thing. By the way, these differences are still, if you're doing a 32-bit user land on a 64-bit kernel, you still get these differences between AMD and x86, AMD and Intel. But that's, kind of a really small detail. And then we stuff the system call number into one of these registers, AX or R0, and arguments in other registers, and that's it, right? And then we issue that syscall instruction. So you can see that happening here. So it's basically the right system call on x86-64 is system call number 1, obviously, and it's just moved that 1 into register AX and done a syscall. And then a few lines above, it's put the buffer that it's writing and the length that it's writing. Okay? So, I just kind of said most of that, right? If you really want to know, you can look in proc. We'll look at proc a bit later, but so we can go, whoops. So what do we get here? Proc, sys, ABI, vsyscall 32. Can be this tells me, from this I can infer that I'm running on an Intel chip here. But really it just tells me how that all works. And basically whether the sysenter instruction is available. Okay. Right. That's kind of the really first kind of simple bit of it. Makes sense. Kind of fairly straightforward. Let's talk about vdso, right? vdso is the virtual DSO, DSO being dynamic shared object, which just means a shared library, right? Anything .so is a dynamic shared library, DSO. But vdso is kind of special. So libc, I've got libc.so on my system, and that's a regular dynamic shared object, right? So libc on the file system, the process maps it in, and along with the text of the program being executed. So again, we can see that. Let's go. Oh, damn. There we go. So what have we got here? So these are all the memory. These are all the virtual virtual address ranges of my process. Actually, I'm going to restart the process because it gets a little bit simpler at the start of day. So this is before any of the setups really happened. So it's really simple. So I've got a.out, I've got the code and the data and the read-only data. These are just memory maps onto the appropriate part of that file, right? I've got ld-linux.so, so that's a special shared object. And then we've got stack and this vsyscall. So I'm going to talk about vvar, vdso, and vsyscall in a minute. They're kind of special. Stack's probably pretty obvious. If I run the program further, now I have a bunch more maps. Some of them look to libc.so, right? So that's the dynamic shared object that is libc that pretty much everything links against. You don't have to. You could handcraft all your system calls if you want to, but pretty much everybody does. But then, yeah, I've got these weird things, right? vvar, vdso, these things in square brackets, and actually there's this vsyscall. They're all kind of the same. They're just newer versions of each other. So the original one was vsyscall, then vdso came along, and then most recently vvar's come along. The kernel, by the way, this kernel user space ABI, by the way, it's really stable. One of the things that surprised me, we've been building undo for it's actually amazingly getting close to 20 years now, and very few times have they made a breaking change. Like we intercept, remember what I said at the beginning, we intercept all of the syscalls and everything else, signals, and it's like we care about where every single bit is. I mean, it's like it must be absolutely precise, and I can think of only one or two times when a breaking kernel change was made that caused us to go, oh, they're really, really subtle to change the user space kernel ABI, and we had to deal with it. In fact, and one of those was a security vulnerability to the Rowhammer attack, and Linus himself got involved in that mailing list discussion pretty quickly, and they provided another way around it. I've been amazed how good a job they've done at maintaining basically perfect ABI compatibility. There's a few things with the way signals work and stuff, but very rare. Yeah, right. And they say that they will only break it for security if it's to fix a security issue. It's kind of the policy.
Or if no one knows.
Right? Yeah, we noticed that one. Yeah, they do. Some of them, I might get to if we get time. Probably not. But the way signals works has changed a little bit over the years, and we have to kind of deal with that. But mostly, the backwards compatibility is excellent. Completely different to Windows, by the way. So Windows makes no guarantee of stability between kernel and user space, and you use the stable layer is between the what's it called, Win32, yeah. So Microsoft make a time travel debugger, which is kind of it's pretty good, but it's much harder for them because even though Microsoft make it Linux has about, I haven't counted, but about 500 different system calls. Whereas Windows has thousands and thousands, and no one knows what they all do, not even Microsoft. And so they had to implement their time travel debugger a bit differently. And even if you did know what they all did, they change all the time. Linux is different. Anyway, so the original one of these magic pages that gets mapped by the kernel into user space was this vsyscall page. Done because we wanted to be able to take a binary and run that on different versions, different AMD and Intel CPUs and things. And is that 10 minutes left or 10 minutes got 10 minutes? Oh my God. Right. Okay. Right. We can talk about that afterwards if you're interested. No one's interested, Greg. Move on. Yeah, no. So, but the VDSO is a little bit interesting if that's your thing. So it's like a libc.so or any other .so that you might dynamically link against, but it doesn't actually exist like in the file system anywhere. The kernel just puts it there, and along with vvar, and it enables you to do things like you can get the time of day without doing a system call, because that's one thing I didn't say. That system call thing into and out of user space is relatively expensive. Much more expensive. Like it's by far the longest, syscall instruction is by far the longest to execute instruction that you'll find. I mean, even if it's a really basic one like getpid, it's still, you're talking like many microseconds to execute. So if you want to do something like get time of day, which a lot of programs want to do quite often, or an equivalent clock get time or whatever, we don't want to call into the kernel all the time. That could be really slow. So what it does is publishes through vdso these kind of helper routines, and they will be kernel specific, and they will get you the time of day without actually having to switch into kernel mode. And there's some stuff in the vvar map which will just update the kind of current counter so you can kind of see where you are. So yeah, that's vdso, and it's kind of cool, I think. Yeah, it gives you portability and gives you performance. Right, yeah. So I mentioned errno before. This isn't really part of the kernel ABI, but if you're writing C code, then it's relevant. So errno isn't part of the kernel ABI. So as I said before, if a system call fails, it will return a negative number. So every system call, actually, any syscall that returns between -1 and -4095, that indicates an error. Okay, so something like mmap could returns a pointer, but the pointer is not going to be in that range, right? That would not be a valid pointer. On those, when the C library wrapper will see the negative error code, and it will invert it because the errno is a positive number, and it will stuff that in this errno global. Except errno isn't really global, right? Errno is thread local, because errno was invented before there was such a thing as threads, which I'll get onto in just a moment. And so then we had to kind of backwards support errno in this multi-threaded world. So errno is thread local, which it depends on the architecture, how thread local storage works, but on x86, it'll use the FS segment register. If anyone thought segments have gone away, well, they kind of have, actually. The modern versions of segments are rubbish. But I'll do another talk on this one day. Segments are awesome, and it's a tragedy for society that we no longer have them, but that's another talk. But we do have this with FS and GS, allow you just to offset any memory access by a certain amount, and so every thread runs with its, usually run with the same value in FS, but essentially their own FS segment, and so that's how thread local storage works. And there is this function, errno location. So when I'm in, this is a single-threaded program, so but it's still the same applies. So GDB knows, by the way. So when I print errno, it actually it does an inferior call under the hood, and it knows how to work out the where errno really lives, which is this thread local address. You may have seen this if you're old. Like this hasn't been the case for quite some time, but if you're old like me, you might think that libc, so the implementation of getpid, used to be static. So it used to be libc would store at the beginning, or probably the first time you call getpid, it would just store the PID in a global variable, right? Because that's the process ID, so it's never going to change. So within a process, so we can just put it in a global, right? And so that's what slightly older versions of libc did until about 6 years ago, I think. Because it just turns out there's enough edge cases around fork, okay? So the process ID is never going to change, but when I call fork and I get a new fork of the process, then I need to update that cached global PID, and that's okay. So the libc authors just like, did that when you call fork. It just reset the cached PID. But then what if you use the contents of this talk to fashion your own call to fork? You call the fork syscall directly without going via libc. Then we get into that's one of the two hardest things about programming, right? Is cache invalidation, naming, and off-by-one errors. So, yeah, I said I'd talk about processes and threads. So, as we probably all know, the difference between a process and a thread is that threads all run within the same process. They can all see each other's memory, and processes can't see each other's memory unless we set up shared memory or something. And you have process IDs and thread IDs, and it mostly works kind of quite nice and simply, except as far as Linux kernel is concerned, there's no difference between a thread and a process. Like, it's all just tasks. And there's a sort of special version of fork called clone, and there are different versions. There are different versions of clone as well. There's clone 2 and clone 3. There may even be a clone 4 now, I don't know. And you give that certain flags about exactly what I'm going to clone or not when I do this fork. So when you just do a regular fork, it clones everything. It clones the address space. It doesn't clone the file descriptor table, actually. We're not going to have time to get into that. But it clones most of the stuff. But you can selectively choose what to clone and what not to clone. And when you create a thread, it will clone, and it will not clone the virtual memory. Right, so the thread is just another process that shares all the virtual memory, and it shares signal handlers, and it shares file descriptor tables, and a whole bunch of other stuff. A lot of stuff talks about this notion of TID and PID, thread ID and PID ID. So you've got, but actually just what we think of as a process, Linux calls a thread group. It's just a bunch of threads that share certain things, or a bunch of tasks that share certain things, and the leader of that thread group, its ID, is the same as the process ID. And the process does mean something in the Linux world, because you can do things like send a signal to a process ID, and it will arrive at a random thread in that process. It's not defined. In fact, POSIX sort of says this. It's not defined which thread will receive the signal, unless you do tkill rather than kill. We spent months and months and months trying to debug something a few years ago, and it was one character. It was kill, or it wasn't tkill, which nearly always sends a signal to the process you want. Anyway, and then very quickly, there's loads of good stuff in proc. Proc's a good place to hang out. Anyone else like hang out in proc? What have we got? Yeah, yeah. Usually it's about, I don't know, but it's kind of fun, isn't it? When you end up having to do stuff like that. Like, so you can see lots of things. FD is quite cool. So FD is all the file descriptors that are opened by that copy of that instance of ls when I ran ls, because I've done proc self fd all there, and then they're actually symlinks. You can also go, that's a symlink to ls that I was just running, right? Pretty cool, I think. Right, so that's all we've got time for today. If you didn't get a chance to enter the awesome raffle, you can do so now. I think we might have like 1 minute left for one question. Yeah, actually, the trouble is when you say one question, everyone's like, no, my question's not good enough to be like the only one. Yes, your question is good enough.
So you said like this virtual space to call get time.
Yes.
Why aren't all the calls to the kernel via this shared object?
Yeah, so the question is, why are only some system calls through the shared object through the VDSO, like get time of day, and not just all of them, because they'd all go faster? Because you need to be able to, it's really hard to make that work, right? You need to be able to give the answer without being able to see anything that you're not allowed to see. So if I wanted to, get some kind of bit of like secret information out of the guts of the kernel, I can't I can't expose that to the user level process, right? So get time of day. I don't know why getpid isn't in there. I think getpid probably will live in there at some point if it doesn't already. There are certain things that it's safe to export from the kernel directly into user space, but most of it, not so much. Okay? All right. Oh, well, okay, one more question.
With i686, you meant 32-bit post-Pentium CPUs, right?
With i686, I meant 32-bit post-Pentium CPUs. Yeah, it kind of probably would be the same for i386 as well, actually. It's just that, like, it seems to always, like, these days you don't see it. It's just called, that's what Linux calls the architecture when it's built most of the time. But for everything I just said would apply to i386 as well as i686. There wasn't anything new. Oh, except for sysenter and syscall instruction only came in at i686. They didn't exist in the 486 or 586.
Okay, and
Yeah.
how about the errno and errno 2? Do you also look into that?
Yeah. We do, yeah.
Based on it?
Yeah.
Like Grandin, for example, or also some
Yeah.
still existing?
So I think Itanium, yeah. It's a question about Itanium, yeah. I mean, I really don't know. I mean, I've never programmed to it. What I've seen of Itanium is it's just wild, and like everything is different, and probably none of that applies. Yeah. So just, someone described it to me, someone from Intel actually. It was like they took all of the computer architecture papers of the last 20 years and just stapled them all together, and that was Itanium. Probably why it didn't work. Right, okay. Thank you very much.